you very much.
I have to disconnect you now because the next speaker is going to use his laptop. Thank you. I guess it's night in Sweden, so with that.
Yes, it's 11:30 in the night, so we wish you a great workshop, and I'm very sorry I couldn't be there because the things are interesting. So have a nice workshop. Bye.
Bye-bye. Thank you. Our adapter is different for every generation, so if you use it, it's
HD, okay, yeah, so that's better.
so some of the audio is
Yeah, here. The next presentation is provided by Chen Wang, and the title is the process documentation and the validation of requirements.
Good morning, everyone. So I'm going to present to you a precise documentation method and how that method makes formal validation possible. That's basically the 2 points I'm going to address in the talk. Just about the introduction of the motivation and background, we all know that, and we agree, the system has to conform to its requirements. Otherwise, it doesn't really matter how brilliant you have done your implementation. You have to build the right products. Especially in your system requirement, it must address both the controller and its operating environment. You have to think about what's the assumption and what's the required behavior for your controller. However, usually, problems and costly problems usually occur in the requirement stage, which make it very late to fix your code if you find any problem in your requirements after your coding has been done. So we have to be very careful. Now, requirements are usually incomplete and ambiguous because they are written in either natural language or they are presented in use cases. So they cover a finite number of possibilities or scenarios, so they can never be complete. Now, we have the industrial standards from automotive, nuclear, or aviation. They recommend the use of formal methods. In our method, we choose a particular formal method called tabular expressions. Has anyone heard about tabular expressions before? Okay, that's why I'm going to give you some introduction to that. Basically, the tabular expressions has been used in practice. For example, in Ontario, in Canada, the Ontario Power Generation Company, they have used the tabular expression to model the requirements and design of the nuclear shutdown system, the Darlington shutdown system. And I'm going to show you very quickly what a tabular expression looks like. So this is the generic form of a tabular expression. So we have the input conditions on the left column, and we have the output value on the right column. And here, we have the conditions C1 and C3. If C1 is true on your inputs, you're going to check if C11 or C12, either one is actually true. Let's say C1 and C11 are true. Then you're going to update your output according to a relation R1. That's actually how you do the tabular expression. And the good thing about presenting your documentation or your specification as tabular expressions is that it is very obvious to it's actually much easier to organize your documentation in such a way that you can argue that your specification is both complete and disjoint. So these are the formal definitions of that. You can refer to the paper, but intuitively, your specification is complete if you have no missing cases for your input conditions. For any arbitrary input that you observe from your environment, you can always have a way to handle that. And also, your specification must be disjoint in the sense that if given some input condition value, you have only one way to actually respond to it. You don't actually have two ways from your table. Let's say given inputs, both C1 and C3 are satisfied simultaneously. In that case, you will actually have to assign your output according to R3 and R1. In that case, you might have contradiction. So in tabular expression, these are the two most important structural invariants that we want to argue about. We actually see an example of the case study. So that's about the tabular expression, and it has been used in the practice. And in our method, we're actually going to use the tabular expression in such a novel way that you can argue global invariance or safety property about your system, which doesn't quite exist in the literature. I want to broaden our context in the context of software certification. Given a precise requirements document, what can you do from it to actually certify your system? We have an increasing level of assurance cases. The lowest one is just to use the requirements document to generate some test cases for your implementation. However, as I said before, to find any bug at this stage, it might be too late. You might have to ship your software tomorrow, and you found a bug today. It might be too late. The middle one is slightly better. We can actually implement some mathematical execution library for programming, such that while you're developing your code, you can actually write contracts for your code, and you can already test your software while you're developing it. So you can actually reveal the defects much earlier than the first one. The third one, which is going to be the focus of this talk, is we can actually do some formal proofs about our requirements documents or formal validation. We think that for 90%, roughly 90% of all your proof obligations, you might just be able to throw it to Z3 or to throw it to some automated year prover, and you can discharge them automatically. However, for realistic projects, about 10% of the proof obligations, they may not be discharged automatically. In this case, we propose machine validated as opposed to machine assisted human reasoning. So we're actually going to do the proof by using human intelligence, and we're going to justify each step of proof by the machine. I will show you once we go to the case study. So let's just go directly into the case study for this paper. So we have a biometric device over here. So it's going to monitor the patient's blood pressure by a column over here. And the input is going to come as a continuous signal for the blood pressure. And the machine internally is going to transform it into a finite sequence of sample plots, sequence of real numbers. And what the machine has to do is to calculate the various parameters or values according to the IEEE 101 standards on transition, pulse, and related waveforms. That's the general problem that we're trying to solve by our method. So this is a diagram copied from the IEEE 101 standard. Let me just guide you through it. So the x-axis here represents the time, and the y-axis over here represents the level of your signal. This is the minimum level, and that's the maximum level, and you can actually calculate what should be the 10%, the 50%, or the 90% level, and the corresponding time instance is called the 10% instant, for example, or 50% instant, or 90% instant. And we are considering a single positive pulse. In this case, we can actually use a unique maximum to actually divide the pulse into two. So this is called a positive transition on the left, and on the right is called a negative transition, if you're negatively going. For that, we also have other parameters. We have the duration of the pulse, which would be the 50% on the negative side, minus the 50% of the positive side. And for each transition, we also have to calculate what's their duration. In which case, let's say for the negative transition, to calculate its duration, we have to subtract the 10% from 90%. Okay, so that's in general how you actually do the calculation. And here I just summarize all the parameters I have just described. So we have some naming convention in our paper. So we use y to represent the level for the y-axis. we use P standing for time instance, and we also use P for positive and N for negative. So just some naming conventions so you don't get confused. Now, what are really the problems that are faced by our industrial partner such that it will motivate our current approach in presenting the paper? So, first, how do they actually deal with exceptional cases of ill patients? So this can be a possible input for the software, which is very different from the classical shape I just showed you in the previous slide. In this case, you can see for the 50% level, we actually have multiple 50% instance, and also we have multiple 10% instance. Now the question is, how should we select from the multiple 50%, and how should we select from the multiple 10% or multiple 90%? That's really the question we're asking. And the second concern is, how can our industrial partner argue to the certifying agencies such as the FDA in the States that their code is actually safe and fit for use? And with respect to, let's say, the IEEE 181 standard, which presumably should be the requirements documents. Now the question is it really a good requirements document? I'm afraid not. We actually found at least 2 ambiguities in the IEEE 181 standard, which we think our approach can really help disambiguate the issues. Just go through very quickly. So there are actually more ambiguity reported in our extended report. The first ambiguity is, if we have multiple 10% and 90% instance, how should we choose? So this is a direct quote from the IEEE standard. If there's more than one reference level instance, you should choose the closest one to the 50% level, otherwise, unless otherwise specified. In this case, the problem is, this description here actually allows the input such that your 90% is actually less than the 10%. Let's not go into very details. The consequence of this is that the duration of the pulse is going to be negative. So this indeed is a contradiction. I don't think the standard is meant to have this to happen, so we found that. What we do as a resolution is we should declare some invariance about the system such that we can argue about the preservation of the invariance. I'll show you exactly how we do that. And the second ambiguity is to calculate the linear interpolation. So let's say, so that's your y, that's your time, because your input is actually discrete, it's finite sequence. Let's say we have T1 at this level, and we have T2 at this level. Let's say these are the 2 consecutive inputs in your signal. Now, we might want to know what's the value for T3. The way to do it by the standard is to do linear interpolation to actually calculate what's the proportion to calculate this value here. So that's what linear interpolation is going to do. However, the formula supplied by the standard has obviously the problem of division by 0 if these 2 values happen to be the same. There's no mention about how you should resolve such situation. So we think we can alternatively present a total function to calculate the linear interpolation. I'll show you exactly what I mean. Okay, so that's the problem we are trying to solve, and this is a summary of our method and contributions in this paper. So given a list of natural language system requirements, somehow we want to formalize them such that the formal validation is possible. So first, we have a list of ingredients for precise requirements documents. I'll go through them one by one. So we have a machine modeling the environment and controller. We have tabular expressions for completeness and disjointness. And we actually define auxiliary queries and organize them into modules and types. And we also have a well-defined theory to make sure all the expressions involving partial queries are well-defined. And we also try to validate our proofs by using the Z3 solver. And we also have the traceability from our formalization back to the natural language description. So let's go very quickly just to get an overview for how our solution looks like. Ingredient before we present ingredients, let's identify, according to Jackson, and also how they actually do the separation between environment and controller in the OPG, nuclear shutdown system. We have a context diagram here for the problem. That's the pulse controller, and we have monitor variables, and we have controller variables. The controller is going to monitor what has been periodically changed in the plant, and the controller is going to react accordingly to update the controller variables. In this case, we are reading from the plant the sequence of real numbers as the sample pulse. And we are trying to react by supplying the report of the parameter values, and we have to report any errors or warnings if there are any. Okay, that's a big picture for the system boundary. And now, it is actually useful to have some informal descriptions before you start formalizing. You have to have some direction as to where you're going. So very quickly, we have two kinds of information, informal constraints. So one is called the environments, or E-descriptions, to document the assumptions about the environments and to put some constraints on the monitor variables. Just to give you one example. So here we say, to be a valid pulse, it has to have at least 3 samples. It must have a unique maximum. You must have at least one 50% instant. And somehow this will be translated into our formalization, into our specification. I'll trace it back once I get there. And the second one is just to say how we partition the pulse into positive and negative. And the other kind of informal description is the R descriptions, which have to document the required system input-output behavior and to document what are the desired properties that you want to preserve on your system. So in this case, we have, oh, by the way, you can see that the R description and E description are numbered. You can make it very easy to actually trace it back from the formalization. So I highlight the keywords just to make it quick for you to read. So we have to define what a valid pulse is for waveform and transition parameters to be calculated. We have to say in which case it should be classified as warning case, and in which case should be classified as error case. Let's not worry about the detail. So you have to know, the only thing you have to know is we have 3 possible R descriptions to be formalized. Okay, and also we have to say, in case where there are multiple 50%, how should we choose? In this case, we say we choose the first one for the positive transition, and the last one symmetrically in the negative transition. And now, we also have to declare some invariance here to say, we want to make sure the pulse duration should be positive always. That's why you see the T90P for the positive is actually larger than T10P, such that the subtraction will be positive. Okay, so now let's start learning the ingredients for precise documentation. The first ingredient is you have to formalize the system behavior by using an event-be-like machine. So over here, you have to say what module you're trying to use, like an import statement. And you have to declare the control variables. In this case, you have 3. Report, error message, or warning message. And this event over here, execute, models the joint action between the environment and the controller. Given any arbitrary value for the input sequence, we have to do the response for the controller according to this external reference of the tabular expression. So here, I just put some reference here. We actually see how exactly the table is defined separately. So exactly what I said. Okay, so now, to actually specify the controller, we have to know what inputs we are reading and what outputs we are generating. So the sample waveform, the sequence, is inputs, and the report error message and warning message are the outputs. And here we have some intermediate calculations to make sure all the applicable parameters are calculated. And also we can, since we're going to use tables to specify the controller behavior, we can easily argue about its completeness and disjointness, as I showed you before. This is all we have to do for the tabular expression for the case study, a real system. So here you can see that we have the conditions rows and conditions column, and we have 1, 2, 3, 3 columns for the outputs. So basically there are 3 kinds of rows. So this S3, UN, T50 question mark, and T10 question mark. So this path over here represents a valid pulse, in which case we should calculate all the parameters. And this part over here is the warning case where we have some parameters undefined. And this part over here means we have some error to be reported. So that's exactly, is precisely specified in the tabular expression. So I just included the whole definition, but to actually understand that, please read the paper. I just want to give you an idea about how we specify the tabular expression. It's a very neat and precise way to document your complex relation between inputs and outputs. Okay? So in the tabular expressions over here, all the abbreviation you see here, they are actually auxiliary queries that are specified elsewhere. So we're going to see how we actually specify them. This is, and we also we actually organize the queries into modules. We have a modular structure for separation of concern. For example, we have module at the bottom over here. Oh, the arrow, by the way, means it depends on the other module. So this is a bottom module. It actually somehow declared a monitor variable. So for the module can, all the variables that are declared in the module is also visible to the modules that depend on that. Okay, that makes sense. Okay, just different modules have different functionalities. So, and also we have a module waveform that actually transform the discrete sample waveform into a continuous total function, as opposed to the linear interpolation by IEEE 181. So that's basically the idea. Each one of them has their own functionality. How much?
Maybe 20 minutes out.
Okay.
We have 10 minutes.
Okay. 5 maybe. I'll be ready.
No, maybe.
We'll see. So over here, so the square box means module, and the module may have to use some type for some other auxiliary queries, but that's basically the structure. Let's just see one example. So this is the pulse module, which uses the positive transition and negative transition modules. And here we have queries, and queries, each query may have a precondition by the required clause, which will make it partial, which means it is not always possible to call this query when its precondition is not satisfied. The result will be undefined. That's why we also need a well-defined theory. Okay, so here we have 3 queries here: error, warning, and OK. And guess what? We can trace this back to the E or R description that we said before, informally. In this case, we can trace back to environments 1 and 2 over here, because we said we actually talk about what a valid pulse is and how they actually partition the positions. And that's exactly how we do in the formalization. So we can always trace back. The more detailed explanation is also in the paper. Please read it if you're interested. Okay, so that's really about how we specify the modules. And so just other modules. And we also declare the invariants we mentioned before in the R description. And let me just skip that because they are pretty much the same idea. And here we are also using some auxiliary function from some type called R-fun, standing for real value function, to actually do the total linear interpolation. And this is the type that we define to model the real function. And this is the linear interpolation, our version. Apparently, it would not be suffering from division by 0, so ours is better. And that certainly can be a resolution to the IEEE's problem. Okay, so this, after we have done the tables, we have done the machines, we have done the queries, now we can start validating our requirements. There are 2 kinds of validation we can do: structural and semantic. Structural validation is really about the completeness and disjointness, and they have well-defined semantics or tabular expression, so we can certainly just do that. Yeah, it's not really our contribution here. Our contribution is really about how you actually can combine all the artifacts together and to argue about some global property. In this case, we have tables, we have modules, and we have types, and we have invariants that we declare in the module we want to prove. So this is some handwritten proof. Don't try to read it, that's fine. I actually highlighted parts I want you to pay attention to. Starting from the invariants, eventually we want to say it is equivalent to true. And we have a number of justification steps. Each one of them actually makes use of the query definition somewhere in our modular structure. And what we have to do is to make sure that it is convincing from our human intelligence point of view. And we are going to actually validate each justification step by using machines. That's actually also addressed in our paper. We actually use the Z3 constraint solver to actually make sure this step is okay, this step is okay, and by transitivity, all the steps together will make sure this is equivalent to true. That's basically the idea. Okay, so basically that's pretty much the end of the talk. I just want to say that there are more in the paper to be explored, especially our contributions also about the theory of well-definedness, because we actually use expressions in the tables that involve partial queries. So that certainly raised the question about well-definedness. So we have defined well-definedness theory in our paper, in an extended report actually. So we actually we have some recursive definition for that, but we actually apply that in arguing that our tabular expressions and our proofs, each step, are WD preserving. And that's actually the formal definition for well-definedness, but it's not really crucial if you understand the technical details at this stage. Okay, and we also include details in the paper about how we actually formalize each proof step into Z3 constraint. So if you're interested, also please refer to the paper. Final slide I want to say is we actually have some extended work beyond this paper. Remember I said we actually got an increasing level of assurance. First one is manual inspection or test. Second one is executable specification. And third one is proof. We have done some work in the second one, and which we actually do some programming library in the IFO language, because IFO has native support for design and contracts using precondition, postcondition, and variants. And we actually have done that, and this is just one example. The only point I want to make here is this corresponds very closely to the modular specification we had before. They have very direct translation into the IFO design and contract framework. So that work has also been done and also reported in our extended documents. Conclusion. We have developed a method for precise documentation for system requirements, which has different ingredients: machine, events, tabular expressions, and we have modules, queries, and types. We also have a theory of well-definedness because we have partial queries. And also we can do validation about the structural and semantic integrity about your system. And our focus now is really the documentation. One of our reviewers actually gave very valuable feedback. It's about the limitation at the moment. So the tabular expressions that we have extended to the event B syntax has not gone beyond the semantic round. We have not extended event B from the semantic point of view. The only thing we have done is to provide a convenient syntax for you to use. And if we want to do more expressive properties, we have to use some other programming theory. That will be the future work. Thanks for your patience. And that's the further references. You don't see other issues. Thank you.
Time to the question and answer. Comment. Okay. Who's the person? Okay.
Can I?
You.
Okay. Sure.
Just to check, so you cannot still write temporal constraints in your conditions, like the duration of some input. When the duration of some input is 20 seconds, for instance,
Yeah.
the reaction should be some.
So the case study we have done is actually a transformational sequential system. So at the moment, we are not able to prove temporal property, especially liveness property. The one we just showed you how we proved that was actually a system safety property. It's like a henceforth, some predicate is always true. That's the only thing we can do. However, since we actually have got a framework down already, we think that's a promising start to extend it to other properties as well. Yes?
So it seems to me one of your problems is converting between the real domain and a quantized domain. So I was having a bit of trouble trying to work out how you can have a slope on a positive thing being negative. Just wondering, could you comment a bit more about, was there any are things that are true in the continuous domain no longer true in the discrete, or?
Okay. Yeah, I think, yeah, thank you for the question. So basically, there are actually two things we are trying to handle. One is the input sequence. So the input sequence is simply something like, so 1, 2, 3, 4 at time. So let's say this is time, and this is the level you have. Let's say 10, 20, 20.5, and etc. So this is the input that the machine is trying to calculate. However, sometimes to actually get the, let's say the 10%, the 10% might lie in somewhere in the middle of here, which doesn't really exist in your finite sequence. So we actually follow the IEEE suggestion using linear interpolation. Yeah, so I think that's the key. Yeah. However, IEEE 181 is very horrible because you might have some division by zero problem, which we don't have. Yeah. Yes.
Hi. You just mentioned you used Z3, which is a central solver, right?
Yes.
So I was wondering, like, is there any benefit of using Z3 over the open source central solvers such as OpenSMT?
Sorry, I didn't get it.
I mean, you used the Z3 central solver by Microsoft, as far as I know, and I think it's not an open source central solver as well. I was wondering, like, is there any benefits of using Z3 other than like any open source central solver? Because nowadays a lot of people are working on open source central solver as well.
Yes and no. Yes, because Z3 is a good thing to use because many people are using it. And Z3 is actually maintaining quite well. It's quite strong, maintaining the features quite strongly. So that's a yes part. No, we don't necessarily have to use Z3 because all we have to do is to encode the proof step into a first order predicate. Certainly you can do that in any machine you like. Yeah, doesn't have to be Z3.
And the input format is simply format for that?
I think so. Yeah, we don't actually create any extra syntax for that. Just yeah.
The time is over. So, I want to thank the speakers.
Thank you.